places, a very warm welcome to the first technical session of the fourth day of this 5-day online short-term training program organized by Department of CSEIT, CSEIML of BCET Durgapur under the aegis of the Institute of Engineers India, Durgapur Local Center, and it is technically sponsored by the IEEE EDS 5-day Kolkata online chapter. Today's short-term training program organized by highly promising area of modern electronics and device engineering titled Programmable Optically Variable Registers and Their Applications. To deliver this lecture, we are honored to have with us Dr. Aritra Acharya sir, Assistant Professor in the Department of Electronics and Communication Engineering at Kollani Government Engineering College. Dr. Acharya sir earned his BE in Electronics and Telecommunication Engineering from Bengal Engineering and Science University in 2007, followed by an MTech with first rank in 2010 and PhD degree in Radio Physics and Electronics from the University of Kolkata in 2016. With over 16 years of teaching and research experience, his expertise spans nanoelectronics, millimeter wave, and terahertz devices, IoT, optoelectronics, and flexible sensing technologies. Before joining Kolani Government Engineering College, he served as an assistant professor at Kuch Bihar Government Engineering College and Supreme Knowledge Foundation Group of Institutes. Dr. Acharya sir has published more than 200 research papers, books, and book chapters and has contributed to several prestigious research projects, including Indo-Japan collaboration and DST-funded initiatives. He has received numerous honors, including the IETE Journal of Education Award, and he is professional member of IEEE and the Institute of Engineers India. He is also a frequent invited speaker and session chair at international conferences. Today, he will share his expertise on programmable optical electronics and their application, a topic that holds significant importance in the advancement of intelligent electronic systems, sensing technology, and next-generation computing platforms. On behalf of the organizing committee, I extend our heartfelt gratitude to Dr. Aritra Acharya sir for accepting our invitation and taking time to be with us today. Ladies and gentlemen, please join me in extending warm virtual welcome to Dr. Aritra Acharya sir. And the platform is now yours, sir. We look forward to your presentation. Thank you, sir.
Thank you for this gesture. I welcome all of you, the participants and dignitaries present here for my presentation. First of all, good morning to everybody. Let me share my screen first. Can you tell me whether my screen is showing or not?
Yes, sir, it is clear.
Okay, let me start, okay? Today, my title of the talk is the Programmable Optically Variable Registers and Their Applications. I think it is a very quite interesting topic, and it is not complicated, okay? It is very simple and easy to understand. If you have the knowledge of 12th class physics, then you can understand that what is the working principle of this particular device. Now, let me start with the introduction. We all know that in the electronic circuits or electrical circuits, whatever, there are two major components. One is the resistor, one is the capacitor, and another is the inductor. Okay. Now, resistors are the most frequently used electronic component for both DC as well as the AC circuits. And in various applications, whenever we want to whenever it is needed to change the resistance value, we use the potentiometers. Potentiometers means on mechanical device which is capable of changing its output resistances by rotating some knob or rotating some mechanical arrangement. By that way, we can change the resistance values. Okay. its applications are various electronic devices like variable gain amplifiers, sensor calibration, or any kind of tuning circuits where resistance variation is required. But in modern day electronics, everything is going to the automation. Okay, automations means there should not be any human intervention. All things should be controlled by means of some microcontroller or microcomputer, whatever. So in that case, the manual mode potentiometers are not compatible because that does require the manual intervention. That means the manual tuning of the mechanical arrangement. That's why one particular device is there in literature that is called the voltage control registers. That means it is a device where input side is the voltage and output side is the resistance. By changing the input voltage, the output resistance can be changed. Okay, that is the concept. It's called the called the voltage control register or VCR. That means it is a device. So there are two types of input side is the voltage and output side is giving the name of those. By changing the one is the digital potentiometer, another resistance can be motorized. That is the what are those? This is called the voltage control register. Just for the device. Can you remember from the practical classes of BTech or whatever in basic electrical engineering? This particular device is called the rheostat. By changing the position of this particular slider, we can change the resistance value. And it is used for the high power circuits, like in the order of hundreds of watts to kilowatts. Okay, so this rheostat device is useful for the electrical circuits mostly. But for the electronic circuits, we all know that we deal with very low voltage and low current applications. That's why its miniature version is the potentiometer, which is used in various electronics laboratories. This is the photograph of the potentiometer, where there are three ports. One is the common. It is the internal structure. There is a weeper. Okay, this weeper is in the touch with a resistive strip, and two terminals of the resistive strips are connected to two other terminals, out terminals of the potentiometer. And if you consider the resistance between these two terminals, then weeper, depending on the position of the weeper, the resistance will increase or decrease. Whatever the amount of resistance will be there, the other part will have the total resistance value minus this portion resistance value. Okay, so it will provide you the potential divider circuit. So by changing the position of the weeper, we can change the resistance of two different ports. But thing is that summation of resistance, all over resistance will be always constant. And its application is low power devices, as I mentioned, in the order of milliwatts to watts. Remember. Now, why the voltage control registers are essential for the electronic circuits? As I mentioned, for the automation in electronic circuits, we have to use the voltage control registers. Voltage control registers have two types. One is the motorized rheostat, another is the digital potentiometer. As I mentioned in my introductory slide. Now, what is motorized rheostat? It is nothing but one simple rheostat having one stepper motor connected to the slider. It is a stepper motor is coupled with the slider. Okay, by rotating the stepper motor, by controlling the position of the slider, we can change the resistance. So it is a huge mechanical arrangement. It does require some external power in order to energize the stepper motor. Okay, and its response is very slow. First of all, because it is made for the high power electronic circuits, not for high frequency electronic applications. Another disadvantage is that it is very bulky and heavy, requires external power, so it is not compatible with the compact and low power electronic applications. So for the compact electronic applications, there is a digital potentiometer. But digital potentiometer is nothing but a controller guided register array, where these two terminals are the N terminals, this one and this one. In between them, there is a registered array. Okay. By switching these MOS switches, that means the CMOS switch, by switching those MOS switches, we can select how many registers will be connected at the output terminal. In that way, we can vary the resistance. But problem is that since it is the register array assisted resistance variation, that's why the continuous resistance variation is not possible. These are the discrete resistance variations. Okay, so output is discrete. That's why the resolution is limited. It is not analog device, and its input control is the 8-bit or 16-bit, depending on your equipment, and output is discrete values resistance, which can be varied from few kilo ohms up to few mega ohms. But the resistance change is not analog in nature or continuous in nature. It is in discrete nature, as I mentioned. Now, for very precise control, very precise tuning of many high precision sensors, we do require analog control of resistance by means of input voltage. So digital potentiometers, although it is commercially available, it does not compatible with those analog requirements, analog tuning requirements. So we need the analog VCRs. So from this particular need, our research is motivated. Okay. So what we have done, it is very simple to understand. First of all, within a closed enclosure, suppose it is a closed enclosure, we have connected one LED at one end, and other end there is an LDR. LDR means the light dependent resistors. You mean, I think you have the knowledge about the light dependent resistor. Light dependent resistor is made of a particular material which is light sensitive compound, like the cadmium sulfide, cadmium cellulide, etc. Or lead sulfide, zinc oxide. Those are also very commonly used light dependent resistor materials. But most commonly and commercially available light dependent resistor material is the cadmium sulfide. Now, if we enclose one LED with an LDR within a closed enclosure, and there is no ambient light interference into it, within the closed enclosure, there must be some gap between LED and LDR, and that gap may be filled by means of some transparent or translucent material, which is called a spacer. As we have named it as the spacer. Okay. So thing is that whenever we give some input forward bias to the LED will start to illuminate light. Depending on its material, it will illuminate particular wavelength range, and that light will be guided towards the LDR through this material, spacer material, and depending on the input voltage applied, its intensity can be controlled. For very low voltage at the input, LED intensity will be very low. As we increase the input voltage, LED light intensity, emitted light intensity will increase. And we know that initially at the dark phase, the LDR resistance is very high. Whenever some light or photons will incident on the LDR, its resistance will start to decrease. And depending on the intensity of the LED is modulated by means of the input voltage, as I mentioned, and that intensity will guide to change the resistance of the LDR. Okay, and that means ultimately at the output port, these two ports are the resistance terminal, which can be used to connect at any branch of the your circuit where the resistance tuning is required. Okay. So by changing the input voltage, you are changing the light intensity, and that light intensity is changing the resistance, and that tuned resistance is connected to your terminal where the resistance tuning is required. So it is the working principle. It is very simple to understand. Now, from the general perspective, you may understand that how can we control the resistance range? That means the minimum resistance up to maximum resistance, which range of resistance we can vary. There are two parameters, actually three parameters. You know that the spectrum of that means the relative response of this LDR is generally limited within the visible spectrum. Okay, visible spectrum means starting from the violet light up to the red light. So we have to use the visible LED here, and depending on the color of the LED, its response will be different. Okay, so that's why LED wavelength is one parameter by which we can choose the range. Next is the transparency of this special material. If you use very much transparent material, then most of the light, most of the emitted photons will not be absorbed here and reach the LDR surface, and that will lead to very low side resistance. That means the very low resistance variation. Range will be in the lower side. And if you use some translucent material, so most of the photons will be absorbed here and very few will reach the LDR. So in that way, we can achieve the resistance range in the higher values. Okay, in the order of a few hundred kilo ohm to mega ohm, etc. So this parameter, that means the transparency or optical properties of this special material, is another parameter by which we can choose the range of the output resistance. And the third parameter is the length of this spacer. We know that as we increase the length, most of the light will propagate through this medium, and a major portion of the light will be absorbed. And depending on that, the resistance range can be achieved. So again, I am recapitulating. Three controlling parameters is there. One is the LED wavelength, second is the optical property of the spacer material, and third one is the length of the device. Now, generally, these 5 types of VCRs, analog VCRs, have been fabricated and tested. Okay. Now, first of all, I should justify why this device is called a programmable optically variable resistor. I should justify their name. First of all, resistor because it is giving one resistance. And now optically variable because we are changing the resistance value by means of changing the light intensity of the LED. Okay, that's why optical variable. Now programmable. Why programmable? Programmable means by using any microcontroller, we can vary the input voltage, and depending on the input voltage, light intensity will be varied. Okay, so by writing a program in a microcontroller, we can change by using the analog write command. I am giving one example. Suppose we are using the simple Arduino Uno or Arduino Nano. For that case, in order to change the voltage output of a GPIO pin, it is actually generating the PWM waveform. Okay, so by varying the duty cycle of the PWM wave, we can change the average value. That means the analog voltage value at an output of a GPIO pin. That GPIO pin should be connected to the anode terminal of the LED, and the cathode terminal should be grounded. Okay, so variable analog voltage can be applied through an microcontroller by means of a code. Okay, so that's why this device can be controlled by using one microcontroller by means of a program or code. Okay, so that's why it is called the programmable. So the resistance variation here, we can make it simply automated or adjustable through the code, or it can be adaptable. It can be adaptive in nature depending on your requirement at any time of the operation of the circuit. Okay, so first of all, what are the types of the POVRs we have tested? AR core POVR, that means in place of the spacer material, we have used simple AR. Okay, next one is the HMG core. HMG means the hot melt glue. It is very common material or common polymer which is used for the a hot melt gun. That is a popular adhesive in order to fix some parts of so plastic parts or wooden parts, even metal parts can be fixed by means of this adhesive, which is not transparent, it is translucent in nature. Okay. Third one is the epoxy TiO2 nanocomposite. Epoxy means the transparent epoxy resin. And this TiO2, titanium dioxide nanoparticles, are mixed with the epoxy in order to tune its optical properties. As I mentioned, it is the second parameter of controlling the resistance. All of these first three are having the circular cross section, but the fourth is the rectangular cross section. We know that for the planar circuits, rectangular cross section is important in order to have compatibility with most of the planar circuit. That's why rectangular cross section have also been constructed and tested. And the fifth one, the DIP POVR chips. That means DIP means dual inline packaged. As we see in our laboratory, most of the IC packages are DIP. Dual inline package means they are pitch between, that means the separation between two pins of the IC is 2.54 millimeter. So those are called the dual inline package. Now, first of all, AR and HMG core POVRs. You see that there is a simple PVC type enclosure. At one end, LED is mounted. Another end, the LDR is mounted. We have taken different lanes of that. These are the AR core. These are the HMG core. HMG means, as I mentioned, that polymer core. And those are tested. Dimensions are given in this table, which are very important. And thing is that by varying the input voltage, within the known input voltage range, the resistances are measured. Okay, and that resistance versus voltage characteristics, as we see from this graph, these red graphs and these symbols, these are signifying the HMG core POVR responses, and these blue graphs are corresponding to the AR core responses. As I mentioned, if you see at the resistance axis, AR core POVRs are having the, sorry, I have given you the just reverse information. This red colored graphs are corresponding to the AR core POVRs, and the blue color graphs are corresponding to the HMG core POVRs. Okay, so since the AR is totally transparent in nature and very small amount of light will be absorbed within the air, that's why very low resistance range can be achieved by using the AR core POVRs. If you look at the resistance axis, by changing the same amount of voltage, the resistance values are very low. But for the HMG core, as we increase the length, the resistance values are increasing. Okay, so that's why we can choose the range by changing either the material inside or changing the length. And these symbols are actually the square, field, circle, field, rectangle or star, whatever. These are the experimental values, and the solid lines are representing one empirical formula which is curve fitted with the experimentally measured RV characteristics, and that curve fitting is achieved within 2.5% of error. So that means for the resistances, always we need to specify one particular parameter, that is called the tolerance. Okay, so in our device we have achieved 0 to plus minus 2.5 tolerance value, which is much better than the commercial resistance tolerances, which is either plus minus 10 or plus minus 5. These are the capacitance voltage characteristics, which is also measured. We obtain sub-nanometer capacitance, and it is very sharply changing with voltage. And since it is the sub-nanometer capacitance values, and depending on the resistance value at which it is set, the RC delay will be determined. And we have checked that depending on the RC delay achieved by this POVR device, it can be operate up to few megahertz. Okay, that means it is moderately high frequency device, not very high frequency device. The third one is this one, the temperature dependence of the resistance. With respect to the room temperature resistance, we observe that if you use the air core resistance, the resistance is highly dependent on the ambient temperature. But by using the HMG core, the resistance values are stabilizes after certain value, almost 50 degrees Celsius, after 50 degrees Celsius. Okay, so air core POVRs are not for high temperature applications, but HMG core POVRs are suitable for the high temperature applications. Now, epoxy TiO2 nanocomposite core POVRs. For that, epoxy is filled with some TiO2 nanoparticles in order to modulate the optical properties of the special material. Here, in order to measure the wavelength dependence of the resistance variation, we have to use the RGB LED. That means within a single LED, three types of LEDs are mounted within a single LED package. Red, R for red, green for G for green, and B for blue. Okay, so it is one particular unit LED having 4 terminals. One is the ground terminal, and other 3 terminals are corresponding to red, green, and blue LEDs. By varying the voltage at this terminal, the intensity of the red light will vary. This terminal, the intensity of the green light will vary, and this terminal, intensity of the blue light will be. Okay, it is nothing but one pixel of an LED TV or LED display, which is capable of generating millions of colors by changing the input bias values in different combinations. Okay, different intensities of this RGB color will be emitted, and in combination of those, different colors can be generated from it. Okay, and here within the structure, this portion is filled with either pure epoxy. Pure epoxy is very transparent, so most of the light will reach the LDR surface. And if you dope the pure epoxy by means of certain weight percentage of titanium dioxide nanoparticle, then its transparency will decrease. And as we increase the dosage value, the transparency will decrease, and we will get in the resistance range at the higher values. So these are the fabricated structure. As we see that this one is the pure epoxy made spacer structure, which is almost transparent, and TiO2 weight percent, when it is 0.125 weight percent, then its transparency is decreased. And as we increase the TiO2 weight percent, its transparency is decreased. And finally, this device should be colored with a that is, its outer surface should be coated with some opaque color, so that the ambient light cannot interfere with the inner operation. So here the nitrocellulose, black pigmented nitrocellulose paint is used to make this absorption layer in order to eliminate the ambient light interference. These are the light propagation through the RGB light propagation. See that it is for only the red color LED, green and blue color LED. So RGB light propagation through the spacer structure for different POVRs having different TiO2 concentration. So we can see that as we increase the TiO2 concentration, light is reaching at light absorption is very high, and it is capable of reaching not very far distance. These are the dimensions of the fabricated POVRs. These are the different sets of POVRs. See that this one is for pure epoxy core POVR having 4 different lanes. This is for TiO2 weight percentage of 0.125 having 4 different lanes. In this way, 5 different nanoparticle weight percentages have been used in order to form the total 1, 2, 3, 4, 5, and each are having the 4 different lanes. So 20 sets of POVRs have been fabricated, and those are measured. So narrow spectrum source control. Narrow spectrum source control means whenever we use to control the resistance by means of a single colored LED, either red or green or blue. Okay, it is called the narrow spectrum source control. Why? Because single colored LED has a very small wavelength spectrum. So since the controlling LED is using a short spectrum or narrow spectrum, that's why it is called the narrow spectrum source control. And now if we use simultaneously these 3 LEDs to control the resistance of the POVR, simultaneous variation of R, G, and B, it will cause to control the resistance by means of wide spectrum. That means here the spectrums of red, green, and blue are merged in order to control the resistance. Okay, so that is called the wide spectrum. And first I am talking about the narrow spectrum source control. But first, the device structure is analyzed, and an analytical model have been established depending on the geometry of the structure, wavelength, POVR, the LDR material, and many other parameters have involved within this analytical model. And finally, this one is one analytical model by which we can predict the resistance value depending on the input voltage. It is the input voltage. Before starting the resistance voltage characterization, we have first checked whether the nano composites are well prepared or not. The TiO2 nanoparticles are well dispersed within the epoxy core or not by means of the field emission scanning electron microscopy, and it is found very good dispersion. Another experiment was done by means of the XRD, that means the X-ray diffractometry, and by means of X-ray diffractometry we can find what are the anatase phases are present within those nano composites. Different phases of TiO2 are observed. As we increase the concentration of TiO2, these peaks associated with different phases are more pronounced. And one thing is that since it is the cylindrical optical fiber structure, that's why the TiO2 filled epoxy should have good optical properties like refractive index, absorption coefficient, etc. Those are also measured in order to fill the analytical model. Finally, this one is the arrangement to measure the resistance voltage characteristics, and these are the resistance voltage characteristics of those all 5 POVRs. Not 5 sets of POVRs, each having 4 length POVRs. That's why total 20 POVRs. Okay. So here the observation is that whenever we want to use low range resistance, then the red colored LED source or red control of the POVR is the most suitable. Next is that whenever we want to achieve very high resistance range, then the blue color LED is the most suitable one. And if you want to vary the resistance with very high resolution, then green color LED is the most suitable. Green color LED, by using the green color LED, we are achieving highest resolution because the LDR response have the peak at the green wavelength. That means the 540 nanometer, which is the wavelength corresponding to the green color source, and at that wavelength, maximum responsivity is achieved at the LDR. That's why the sensitivity of LDR at green light is highest, and that's why the highest resolution tuning is achievable by means of the green color tuning or the green LED control. Wide spectrum source control, as I mentioned, when three sources are varied simultaneously, at that case we have modeled our LDR as a parallel combination of three different conductances, and these are mutually isolated. First conductance is corresponding to the red light, second conductance is corresponding to green, and third one is corresponding to the blue light. And by using the analytical formula for single colored conductances and finally adding them in order to form one overall conductance, we can model the resistance or the conductance of the POVR for the wide spectrum source control when the three different LEDs are operated simultaneously. Now, again, these simultaneous LED control have been used to measure the resistance variation for different modes, and we have achieved here. See that these are the three-dimensional plots because the input variables are now three input variables are there. Okay, one is the voltage across the red LED, voltage across the green LED, and voltage across the blue LED, and depending on the size and color of the these circles, we can interpret the value of the resistance. These are by using the wide spectrum source control or simultaneous control of the RGB LED, we can achieve much more wider range of the resistance. This is the summary of the entire investigation, and these are the achieved minimum and maximum resistance values for different devices having the different special lengths and different TiO2 filler concentration in the special material. As I mentioned in the first phase, there is an compatibility issue with the modern day electronic PCBs where the circular cross-section devices are not compatible. Okay, these are the circular cross-section devices. These are not compatible with the modern day two-dimensional or multi-dimensional PCBs. That's why we have to fabricate these POVRs in the planar form or the rectangular cross-section. I should show you that. I will not discuss in detail the rectangular cross-section POVR. These are the rectangular cross-section POVR. Very simple, just change the cross-section of the enclosure from the circular to rectangular. That will give you the rectangular cross-section POVR. And next one is the DIP POVR, dual inline packaged. Just like the IC packaging, we have packaged the POVRs by means of DIP packages. See, there is one DIP chip containing 12 POVRs. That means within this IC, 2 POVRs are present. Within this IC, 3 POVRs are present, etc. By integrating multiple number of POVRs within a single chip, we can achieve these DIP packages. So development was started from this one. That means simple translucent core POVR up to the TiO2 epoxy nanocomposite POVR, and finally we have achieved DIP packaged POVR, which is ready to sell and ready to use for your applications for different sensor calibration application, robotic application, etc. These ICs are ready to use. Now, future work, which is very relevant for the computer science students. See, for the POVRs, whenever the source control is done by using the RGB LEDs, three variables are present: red, green, and blue. Okay, corresponding voltages and corresponding voltages. Other two parameters are the TiO2 loading and the spacer length. Okay, if we consider these five as input parameters of a neural network, as per your choice, whatever the type of the neural network, anyone can choose it, and the output of the particular network model will be the resistance value. Okay, first experimentally measure this input output resistance values by changing these input variables, and make a data set and divide that huge data set by means of two portions. One is the 70% used for the training and 30% used for the validation. And after that, train the model. After training the model, just validate by means of the 30% data set, that means disjoint data set. And after that, whenever this trained model is available, that trained model can be used to predict any resistance value depending on the choice of the input parameter. That means for the electronic circuits, when we do require a particular resistance value to be applied to a particular branch, then this resistance value will be considered as a target resistance value. And depending on the target, this neural network model will predict what are the input sets to be applied at the input of the POVR set, so that the target resistance can be precisely achieved. Okay, and that can be made totally automated and replace the analytical modeling, because as I showed you in previously, analytical model will give you plus minus 2.5% of error, and we are now using the neural network models in order to reduce that particular error margin below 1%. Okay. So applications of POVR, I will just show you some applications. You can easily apply these POVRs to any other electronic circuits where the resistance modulation is required. One is the 20 notch filter, which is very important for the biomedical applications in order to eliminate the power line interference at the 50 Hz. Okay, so this particular notch filter is used for eliminating the low frequency, very low frequency noises from the ECG, EEG, or this kind of biomedical sensing or data acquisition systems. Here, this is the 20 circuit, but 3 resistances are used and 3 capacitances are used. In place of the fixed value resistances, we have used POVRs in order to change those by means of external voltages. Okay, so if you able to tune those resistances to particular values so that the notch frequency can be precisely tuned. Okay, if you show the results, we have perfectly tuned the notch frequencies to 20 Hz, 50 Hz, 100 Hz, and 200 Hz, etc. These are the magnitude response and these are the phase responses, and those experimentally obtained values are perfectly matched with the analytically obtained values. Analytical obtained values are actually generated from circuit simulation tool like PSpice, Canard Spice, etc. So these are achieved very precisely. Second application is the programmable optically variable potentiometer. As I mentioned in the previous, at the first slide, the potentiometers are the very commonly used mechanical variable resistance. By changing the wafer, by changing the position of the wafer, we can change the both side resistance values in order to form a potential divider circuit. So by using two parallelly connected POVRs, we can achieve this operation. And this one is that application. See, there is a microcontroller ESP32 which is controlling the input voltage of the POVR by means of the filter. These are the low pass filters by which we are converting the PWM waveform to equivalent DC voltage. Okay, and that DC voltage is applied to the input LED side of the POVR, and depending on the uh, um, voltage value coded here, voltage value applied here within this GPIO, we can change the intensity of the light, and adequate resistance can be achieved here. Okay, which is applied to the two terminals of the two POVRs are there, which are controlled by means of these two GPIOs, and depending on that, R1 and R2 at the output terminals will be achieved. So these are the characteristics. Resistance voltage characteristics of one side is showing as the blue graphs, other side is showing as the red graphs, and these are the residues of the resistance values with respect to the analytical model. And here we have achieved lower than 1% of error, okay, which was our target in order to reduce the error. Third is the automated transistor biasing circuit. We know that for the fixed bias circuits or potential bias circuits, four resistances are values are very important for biasing a particular transistor in order to achieve, suppose, amplifier application or switch application, whatever. The resistance values are very important. Most of the cases, fixed value resistors, fixed value resistances having very high tolerance values are not sufficient to achieve very precisely controlled gain of the amplifier. That's why POVRs are used in place of the fixed value registers, and it is controlled by a microcontroller. See, that's Arduino Uno, and we can achieve very good precision of transistor biasing, whatever. So this one GUI, graphical user interface, which was controlled from a machine or PC by using the user. User will just input the resistance values, and controller will calculate what should be the input voltages to be applied at the input of the POVR, so that these resistance values can be achieved in the transistor biasing circuit. And depending on those, the measurements will be automatically done, and it will show you the transistor characteristics as well as the biasing analysis and your operating point. Okay, so GUI is prepared in order to perform the automated transistor biasing. In with these are a few applications, as I have shown you that students are also working on various other applications like inverting, non-inverting amplifier circuits having variable gains, or differential amplifier circuit having variable gains, etc. By means of POVRs. Okay, so I'm not going through the conclusions. This work is still going on, so it is not time to conclude. You can also contribute your knowledge to this particular field in order to achieve different types of POVRs or more applications you can try. This is the list of publications, references. Thank you. Is there any question from the, now I am welcoming the question from the viewers end. Is there any question? Actually, programmable variable register, most important application is the sensor calibration. Most important application, okay, and particularly where the intensity modulated sensors, where the voltage output value is important. Okay, in those cases, the POVR is the most important. Yeah. If you want to, so suppose you want to, mm, as I mentioned, one thing, the AI can be used to model the POVR also. Okay, that means in better way in place of that analytical model. Another thing we have to think about, what are the applications where suppose you want to make one circuitry, okay, large circuitry, where by which you can physically make one neural network. Okay, in those cases, those weights can be uh, modulated by means of the resistance values or some potential divider circuits. Okay, for those cases, multiple POVRs, more than hundreds or 200s, can be used for realizing large neural networks in hardware. Thank you. Thank you. Yeah. 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 Sure. 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 Mm. Yeah. 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 Actually, the absorption loss, coupling loss, and all optical losses like the scattering, etc. We have to take into account. Okay, but the dielectric loss is associated with the electric field or magnetic field, whatever. It is not associated with that. We are talking about only the optical losses. Okay, so those has to be included in our model. Those have been included. Thank you. Yeah. Thank you. Thank you. Thanks to everyone. Thank you. Thank you.
Thank you, sir.
Thank you. Thank you.